Good morning. We will begin by reviewing classification of landslides. Classification is important in order to organize our thoughts. Landslides are complex phenomena, and the various types of landslides behave differently. So it is very important when we do research or practical work that we understand what landslide type our work relates to. Most landslide classifications, starting from Balzer in the 1880s in Switzerland, divide landslide problems into main types according to the kind of motion that facilitates displacement. And this summary here comes from the reference by Cruden and Warnes from 1996. The first one is fall, where the movement affects a rigid piece of rock which moves down the slope by bouncing and rolling or falling free. The individual rock particles do not influence each other. They interact with the substrate, but do not flow as a mass. Generally, rock falls are quite small in magnitude. The second class is topple, which involves overturning of columns of rock or soil separated by steep discontinuities. The third one is a slide, where movement occurs along well-defined boundary displacement discontinuity or sliding plane, with the sliding body itself having only a limited amount of deformation. The fourth one is a lateral spread, which is a movement resulting not so much from displacement of the sliding body, but from spreading, from its changing shape, becoming longer. Some experts prefer to include lateral spreading under the sliding class because most slides involve some degree of internal deformation. And finally, the flow is a type of movement where the landslide body changes its characters and becomes fluid-like. So flow involves deformation of a fluid material over a rigid bed. The most popular classification in the English-speaking world results from the work of David Warnes that was first published in 1958 in the Transportation Research Board publication on landslides. Warnes updated his classification in the subsequent edition of the Landslide Handbook in 1978. And it is the 78th Warnes classification that is becoming a bit of a standard in the English-speaking world. It was updated by Cruden and Warnes in 1996, but many people, including myself, prefer the 78th version. In this classification system, the type of movement is exhibited in the line headings, falls, topples, slides, spreads, and flows. And in the other dimension, we have material, including bedrock, debris being mostly coarse material, and earth being mostly fine material. Within this taxonomic matrix are fields within which individual slide types are defined by keywords such as debris flow or debris avalanche or rock slump. In this table, I designated with italics those types of sliding that are likely to be extremely rapid, whereas the ordinary letters indicate types that are likely to be slow. I think that the taxonomic framework shown by Varnes is not really necessary, and it leads to some somewhat controversial results, like, for example, having a phenomenon such as debris flow in the same box as soil creep or solifluction, even though those two types of movements are widely different. So I prefer use of the keywords without the taxonomic framework, and I'll show you how that can be arranged shortly. The third dimension of sliding in the Varnes classification is velocity scale, and this is shown here in a form updated from Varnes 78 by Krunen and Varnes. You'll see that there are 7 classes ranging over 10 orders of magnitude. The most important distinction is between extremely rapid and very rapid, which is defined as 5 meters per second. 5 meters per second approximates the speed of a person running. So the extremely rapid slides are those that kill people, that don't allow any reaction. Some of the other human responses to landslide velocity are indicated in this last column. That actually originally comes from my thesis back in 1980 at University of Alberta, where I looked at a number of case stories and found descriptions of human response with records of landslide velocity. So for rapid and extremely rapid, generally no response is possible, except perhaps for people to run away. The slower velocities allow evacuation, either by persons alone or sometimes by people with their possessions, leaving permanent structures behind to be damaged by the landslide. Finally, for the slowest velocities, it is often possible to maintain structures such as bridges and roads on top of the landslide and adjust them or maintain them to accommodate the slow landslide movement. Finally, in the extremely slow category, we have some slow creep-like movements, for example, like those at Lugnes slope here in the Alps, where villages and houses can exist without being disturbed in any significant way. Krunen and Varnes provided some useful terminology, and this was some main morphological terms for a landslide. The most important term probably is the surface of rupture, which is the surface that separates stable ground from the mass that has moved. At the top is the crown of the slide, the main scarp, the head of the slide. Then we have minor or internal scarps, and the displaced material here moves over landslide path into the deposition area, and this here is the toe of the deposit. There's also a toe of the rupture surface itself, which is often covered by deposits. There is a zone where material was removed, and there is a zone where material was added. This is called zone of depletion, zone of accumulation. One term left out by Krunen and Varnes is the source, the landslide source. And I would define that as the space between the surface of rupture and the original ground surface. So that's the original source from which the landslide began. If you look at the landslide source from above and see it in plan, this would be referred to as the source area.
Before we get to the details of classification, I'd also like to clarify some concepts relating to sliding. The sliding mechanism is very important because soils and rocks like to fail by sliding. That is the preferred sliding, where the slide moves down as a block. A good example would be bowed out. We have rotational sliding. And what do these two have in common? This one rotates out, right? The sliding where it moves out. What is the same in both cases kinematically? What would you say do they have in common? Translation and rotation. Little or no internal deformation. Okay, in both of these cases, it is kinematically possible for the sliding mass to move even quite substantially without deforming. So, for example, this tree initially doesn't know that anything is going wrong. It's just riding, and the body of the slide beneath it is intact. And the same with this tree here. It doesn't really know that anything bad is happening, except that it's being tilted. The only thing it recognizes is tilting, but the sliding body can remain intact. And therefore, the mechanics, the internal mechanics of the slide does not play an important role in the mechanics of the landslide. And the landslide can be analyzed using rigid body mechanics, basically. So those are the two rigid slides. But this one is different. Here we have a kind of a combination of rotation here and translation. We have a sliding surface that's neither linear nor circular or rotational. And so in order for a sliding movement to be kinematically possible, there has to be strong deformation. And John Hutchinson some years ago called these compound slides. So that's a very useful term to distinguish from the other two, because in case of compound sliding, you can no longer say that the internal strength of the sliding body is not relevant. It does become relevant, and the internal strength of the sliding material begins to play a role in the mechanics of the slide. The existence of internal deformation is usually quite clearly shown in the morphology of the slide. So where the rotational slide had a very prominent main scarp and a kind of a characteristic back-tilted bench here, those were the main deformation features that you could see. Now we have a main scarp that's quite limited, often very limited, and in front of it there tends to be a depression called grabe, and then its brother, the horst, is a upstanding block that has sometimes just moved forward without much sinking at all. And then there are many internal shears showing the internal deformation of the sliding body. So you can, once you recognize these features, grabe, horst, and multiple internal scarps, then you know that you're dealing with a compound slide. So finally, we get to the Hungr classification. This is not Hungr classification, this is Warren's classification, interpreted by myself. Because, as I say, I do not like the taxonomical framework that Warren started from. So now this classification just lists basically Warren's keywords, just like this in a list. They are somewhat differentiated here in that we have slides in rock and soil, we have falls and topples, and finally we have flows. But these, as far as I can gather, these keywords cover every landslide that's ever happened on Earth. There's only 17 of them, so it's not a very complicated system. I should also just explain one thing. If by a small shallow slide somewhere on a hillside. The slide becomes flow-like and turns into an avalanche. And then it may enter a stream and incorporate water and flow as a debris flow, and then deposit, and then following it, perhaps there is a very strong flood, sediment-charged flood. So the final stages could be called a debris flood. So the slide goes through 4 different stages: slide, avalanche, flow, and flood. So Hungr and Barnes would propose that we have to use all 4 names in a row to describe this event. But that's not a very practical suggestion. For example, imagine you get a paper that describes a certain event that you want to file it in your filing system. So where should you put it? Should you put it in the file where the debris flows are, or where the debris slides are, or debris floods? You have to make a decision at that point. And so the decision is that take the most significant episode, the most significant segment of the chain of events. And because in this case it's obviously the debris flow, the long travel episode through the path into the deposition area, so the paper will go among debris flows. And that's how this classification is to be used. You select one of these keywords to describe the whole event with all of its complexities, and that's where you put it. You don't try to, for example, the class complex that Barnes had in this classification is useless, because if you had a filing in your filing system, if you had a file for complex landslides, probably 95% of all your papers would be in that file. So what's the point of having a filing system if all the files, all the papers are in one file? You have to make some decisions, some simplifications. So the rest of this lecture, I will be going through these individual keywords and illustrate what's meant by them. And also, I will try to provide definitions. So, for example, when I say clay slump, I would like to give you a definition of what is meant by the term. And that really is a kind of a precise way of defining a classification, that each term is rigorously defined. So if you want to translate the classification to another language, all you need to do is to translate the definition. And it doesn't really matter what the name is. It doesn't matter whether you call it Moore or Moorgan or debris flow or boule de bois or boue or whatever. As long as we know how it is defined, we can get back to the basic concept. So, translational rock slide or wedge slide. So these are the planar failures. This small one here in rock. They're planar because they're structurally controlled, defined by some kind of basal plane. In case of a wedge slide, they're controlled by 2 planes coming to an intersection, but they do have one thing in common, in that the failure is translational and very little internal deformation is necessary for the block to start moving. So here's the definition: sliding of a mass of rock on a planar rupture surface or wedge of 2 planes with downslope oriented intersection. Rupture surface may be stepped, as shown over here. These kinds of steps do not introduce internal deformation, so they do not violate the concept of translation sliding. There's no internal deformation. The slide head may be separating from stable rock along a deep vertical tension tract. landslides in existence. Golda, for example, in its initial stages was a translational rock slide, although it later became flow-like and turned into a rock avalanche. So I think I will put the Golda case history into my rock avalanche files. But I would also understand that the initiating mechanism in that case was translational sliding. So if you have a paper about Goldau dealing strictly about the initiation mechanism, you would put it into translational slides file. But if you have a general paper about Goldau, you put it into rock avalanches because that's the most significant thing about it, how far it traveled and that it was flowing. Also, the Seymare landslide in Iran, in the Zagros Mountains, is a translational rock slide that turned into a rock avalanche. The crown of the landslide is 16 kilometers wide, and the volume, I don't remember the volume. Do you remember the volume of Seymare? Yeah, some cubic kilometers. It's one of the largest landslides in the world. So the translational slides are quite important. Here's a rock slump. You can immediately recognize it with the distinct main scarp and the back-tilted bench here. And you can see that the sliding body is quite intact internally. There are no internal shears. So in cross-section, it would look something like that. And it's kind of interesting that this picture comes from northeastern British Columbia. The cap rock is sandstone, and underneath are some Cretaceous shales. Whereas this diagram was prepared by Dr. Malatre from PHM, and it comes from a place called Nantua in the Jura Mountains. So very similar mechanism. They're rock slumps. Sliding of a mass of weak rock from a cylindrical ellipsoid or rupture surface, which is not structurally controlled. There's little internal deformation, and they're usually slow. Not always, but quite often rock slumps are slow. Hard to say why. I could lecture on that for a while, but they do tend to be slow. And here is an example of a compound slide from the same area as the previous rock slump from northeastern British Columbia. So what we have here is a kind of a nearly horizontally layered sequence of Cretaceous rocks, mostly shales, capped by sandstone at the top. And somewhere near the base of this sequence, with near the contact with the Jurassic, there must be a very weak surface. It's probably pre-sheared, and it probably contains bentonific magnetic place, because the friction angle of that surface is about 8 degrees. And we found that by back calculation, by back analysis, this surface has to be 8 degrees, otherwise it could not fail with any reasonable assumption of flow pressures. So you can see the kind of circular part back here with the graben and horst, and then the long central part, which is probably shot through by numerous internal shear surfaces. So as a result, the sliding body is completely fragmented and broken all the way down to the top. So that's a compound rock slide, sliding the mass of rock on a rupture surface consisting of several planes or a surface of uneven curvature. So that motion is possible only if accompanied by significant internal distortion. Again, it has structural control. That's why it's like that. A weak rock like this, if there wasn't structural weakness that controls part of the rupture surface, it would fail in a rotational fail. But the presence of that weak surface gives it the compound character. It can be fast or slow. Actually, actually the most infamous landslide of the Alps, the Bayonne slide, 1963, must also be called a compound failure. The reason for it is because the failure, the rupture surface, was totally structurally controlled. It occurred along bedding planes, and the bedding planes are folded so that they're not cylindrical, they're not rotational. So in order for this mass of rock to move on this curved surface, it had to fail internally. And it had to develop a kind of thing called Frankfurt wedge. And I think Professor Eberhard will mention this mechanism in connection with modeling, because your model is not good if it cannot account for the difference between the low strength of the main rupture surface, which in case of Bayonne again was something like 9 degrees friction angle, no cohesion, contrasting with the high shear strength of the dolomitic layers sheared across bedding. So a lot of the resistance to motion in case of Bayonne came from internal strength. And that, at least Professor Hutchinson thinks that that actually was the reason why the slide ended up to be brittle, because while the rupture surface itself was weak and would have probably tended to fail in a ductile, slow manner, when the interior of the slide was crushed, it was failure of strong rock in shear, which tends to be brittle. There's also a three-dimensional effect in case of Bayonne, which added to the brittleness. But I will talk about that now. Now, here is, we often use devices to somehow get over complexities and difficulties in landslide classification. And it all sounds very easy in the textbooks: rotational, translation, structurally controlled or not structurally controlled. Now, what about this slide here? This is from Vancouver Island. We're looking at some marble and diabase intrusions. So basically a strong rock, very steep slope, oversteepened by Pleistocene glaciation. And a chunk of it peels off. And I'm sure that most of you are from the Alps, so you've seen many cases like this. Just this piece of the mountain just was not right, and it failed. So what is the rupture surface made up of? Is it structurally controlled? Well, it must be, because this rock is so strong. This is a rock that has a uniaxial compressive strength of about 100 MPa. So a slope a few hundred meters high will easily stand unsupported. The only way it can fail is if discontinuities play an important role. So it is structurally controlled. But what is the structure? The structure is a mess. The structure consists of some stress relief joints, some minor faults, some tension cracks, maybe some contacts, a whole collection of discontinuities. If you did a stereo net of this, you'd probably find that it's very consisting of a number of randomly oriented discontinuities separated by segments of impact rocks. Taylor mechanism is complex and often difficult to describe. Some coupling may also occur in this very sudden and extreme rapid. Here is another example of a rock collapse. This is a deposit of volcanic breccias in a quaternary volcano in British Columbia. You can see the breccias layered like this. They don't really have any proper joints, but they're kind of granular. And only slightly welded. And chunk split out of this, of a few million cubic meters in volume. All you can call it is a collapse. It wasn't a translational failure, it wasn't a rotational failure. Just a kind of complex failure of a heavily fractured rock mass. Okay, so that deals with slides in rock. Let's briefly mention slides in soil. In soil, we also get rotational soil slides or swaps. And again, you can recognize them by a prominent main scarp and backtilt. You can see some of these trees have been backtilted. Little internal deformation. They're often slow unless you are in place. There are so-called sensitive places, and I'll mention those a little later. So that's a rotational slow slide or plate slump. We also have compound failures in soils. This unfortunately is photograph didn't come out very well in this slide, but you are looking at a rather gentle slope here formed on the body of a river in the Canadian prairies, just out of the foothills of the Rockies. And at the head of the slide you can see graben, and here is a detail of the graben. You can see the main scarp, the graben, and the horse rises over. And then the broken up, heavily deformed body of the main slide going down to the river. All of this happening in plains of Pleistocene age. And in the distance, you can see that practically all of the riverbanks in this area are formed by this type of compound sliding, and forms these extensive slide terrain features. Now, debris slide. Debris is coarse material, and generally coarse materials are frictional. And tomorrow, I think we'll be talking about stability analysis, and we'll be going through some of the theory of sliding in soils. And what you'll find is that frictional granular materials tend to fail by planar translational failure, as opposed to cohesive materials that they tend to fail in a deep-seated rotational manner. So it's not a surprise that debris tends to fail as a kind of translational slide. Often debris slides developed from the characteristic stratigraphy, where you have a strong substrate that is forming a steep slope covered by a thin weathered material. So this example here, we're looking at granodiorite bedrock slope. Slopes are obviously stable, although they're steeper than 35 degrees, but they're covered by a thin veneer of colluvium and organics formed over centuries by the forest. And here, because of the undercutting caused by a logging road and heavy rainfall, the thin colluvial veneer has slid into glacier. Then often these debris slides become still have half an hour to cover the text. So let's just quickly mention the special categories of fall and topple. These are mostly body movements, and you can see that in action here. This is a picture I took a few years ago hiking in the Yosemite Valley in California, and we heard some noise, and we saw this cloud of material coming off the hillside, and when you look at it, it looks like an avalanche. It looks like some really large body of rock is moving down the slope and destroying everything in its path. This is about 2 kilometers away, so the scale of it is quite large, actually. So there are some trees here. And you would think by looking at this picture that all of those trees are wiped out. They're just gone. But actually, after the cloud dissipated, the area here that we see under the cloud is this area here. And what you find is that many of the trees actually have not been hurt. The tree cover really hasn't changed very much here from what it was before. And that is because this is not really a coherent slide. This is not a coherent avalanche. All that's happening here is that a group of boulders are jumping and rolling. And what you see is a dust cloud all around it. You're looking at a whole bunch of dust. If you were to vacuum away the dust, you would just see several large fragments rolling and jumping through the forest. So that's how we define rockfall. Detachment, fall, rolling, and bouncing of rock fragments that interact with the slope, but they don't interact with each other. They don't flow as a mass. Usually of small bodies. Usually rock falls are just a few cubic meters, and maybe up to 1,000, 2,000. But when the rock slide has a greater volume, then another thing happens, and the fragments then tend to travel together in a flow-like manner, and we're talking about the rock avalanche. Topple, block topple is a simple overturning of a book on a table. So this is in New Mexico. Just this kind of there's some sandstone sitting on a marley foundation, and you can see that this block has already separated from the parent mass and is gradually tilting until one day it will topple over. And the blocks in the foreground actually belong to another block that had gone through the same process previously. The U.S. Geological Survey monitored that one. They monitored the gradual tilting until one day, bang, and the whole thing fell. Here is a more complex set of block toppling failures in a jointed cliff in Czechoslovakia. So these blocks have toppled and fallen down. What's important about block topple is that it is a brittle mechanism, and you can imagine that if you pick a book and put it here, it will stand upright. It's a big book. Then you push on it and tilt it. So at first it will resist tilting. It will resist until you get it into the point of disequilibrium. And then the process is stoppable afterwards. The more it tilts beyond the point of equilibrium, the more unstable it is. And so it's definitely a brittle process. Block toppling will lead to rapid detachment. On the other hand, flexural topple is another thing. And I think somewhere in the course will probably be Eric that will show you a mode of analysis of flexural toppling. Flexural toppling occurs in rocks that are very thinly jointed, and where there's an insufficient much by their base stability, but by friction between them. And also, another thing is that the major principal stress in a flexural toppling slope is approximately parallel with the slope surface. And you can imagine, if you have two blocks like this, you hold your hands together, try to rotate them, there is certain resistance. And the resistance increases with the rotation, so that and that can be shown theoretically, that the flexural toppling mechanism stabilizes itself. It's a self-stabilizing mechanism, similar to rotational sliding. Translational sliding is not self-stabilizing. As a translating block moves forward, it is remains just as unstable as it was at the beginning. Rotational block, as it moves forward, the downslope component of gravity decreases. So eventually, if the movement is slow, a rotational block will self-stabilize. Similarly, a flexural topple becomes more stable as it moves. So many flexural toppling slopes remain stable for long periods of time. You can clearly see the occurrence of toppling on this ridge by looking at these anti-slope scarps here. So these layers are rotating forward, but in a slow manner. And sometimes